This has been a wonderful set of presentations, and the overlap with my own career with many of these individuals is very interesting. But let me start by introducing myself. I'm Sarah Raiella, and I have had a 40-plus year career as a faculty member and administrator at 3 different universities: North Carolina State University, Mississippi State University, and Iowa State University. So all, for those of you who may not know, in the land grant tradition. I'm not quite sure how that happened, but it's been a fascinating career. I retired as Dean of Engineering in 2019 at Iowa State University, a very large college of engineering. My background technically is as an electrical engineer. All my degrees are in electrical engineering. And my research focus was in image processing. And you talked about Kalman and the Kalman filter. Well, my PhD dissertation was on the use of the Kalman filter in image restoration. So how do you improve the quality of pictures? So a wonderful connection in that regard, and we've overlapped in other ways as well. So early in my career, I benefited from National Science Foundation funding. I was a co-founder and later director of an industry university research center. So my work early on not only focused on fundamental research, but also applications to industry and government. And we were one of the very early IUCRC programs at NSF, and it lasted for many, many years. So our focus was in communications, that is digital communications, and signal processing. So my work in imaging fell right into the scope of that particular research center. And my work focused on a number of different aspects of image processing at that time. It was very early on in the early 80s when we started. But much of the work in the center actually has led to things we've talked about today in terms of technology. Certainly led to high definition television, to cell phones and video technology, our teleconferencing capabilities, the internet. I was fascinated in the conversations with Susan with regard to TCP and the early internet connections and protocols, because that was some of the work some of my colleagues were doing in the center. But one of the other areas that I focused on was in medicine. So how do you use the imaging technology in ways to improve the quality of imagery for medical applications? And that led to a variety of work with MRIs and other technologies in medicine. Interestingly, fairly early in my career, I too had the opportunity to have an NSF visiting professorship for women. So Gilda, not only did we share the same graduate program at Rice University, probably a decade before you, I had a VPW professorship, with certainly help in my development as a faculty member and later as an administrator. Another set of NSF-funded projects I just wanted to mention in terms of my own background were the engineering education centers. And these were funded by the National Science Foundation in the predominantly the 90s. They were coalition networks that focused on how do we improve engineering education. So later in my career, much of my focus has been on engineering education, on broadening participation in engineering education. How can we, and what do we need to do to provide learning environments that are suited to all types of learners and all types of people from different backgrounds? I helped to start a Women in Science and Engineering Living and Learning community at NC State and the Women in Engineering K-12 outreach program in one of my administrative roles, and it's really made a huge impact on universities' ability to, as certainly Gilda and others have mentioned, nurture and provide communities for groups that are underrepresented. Another piece of the focus on that was in faculty development. So that's another area that I've focused attention. And in fact, just in the last week, have a new NSF project funded where I'm co-PI with Jackie El Saeed at American Association for Engineering Education, focusing on deans and the role of faculty development. So the one last thing I'd just like to mention is that I did serve on the NSF Directorate of Engineering Advisory Council, invited by Pramod to serve on that advisory council while he was serving as assistant director of engineering. And that advisory council really, I think, provided insights and guidance and certainly feedback to NSF about the kinds of things that were being looked at in terms of supported programs, what was working, what was not working. We focused a lot of attention on broadening participation in our discussions, and over the years served on many different review panels and committee of visitor assignments for the National Science Foundation. So there's lots more I could probably talk about, but I don't want to take all of the time in terms of allowing us plenty of time for discussion. The one person I would like to share just a little bit of information about you we haven't heard about yet today, but I think is somebody we ought to certainly remember and think about. And although Millie never got her Nobel Prize, which I think she deserved multiple times in her career, Frances Arnold did in 2018. And Frances was a pioneer in engineering biology. And she was the first woman in engineering to receive the Nobel Prize. If you don't know about her and her background, I encourage you to look up on the web her information. She has a fabulous set of contributions. She's a fascinating person. Her career has been at Caltech. And her early support came out of the National Science Foundation in chemical engineering. And there's so many other people we could talk about that. Let me stop here at this point and ask Ed, should we ask questions at this point of our participants?
Yeah, so we can ask questions. Let me just make one. I had the pleasure of Carnegie Mellon this past graduation gave Frances Arnold an honorary degree, and I had the pleasure of putting her as a trustee. So I agree with you that really a remarkable researcher and scientist. So that was the first time I got to hit a Nobel Prize winner. Yeah, I think what we're gonna do here is Professor Hammond's gonna show up in about 10 minutes. So when she shows up, we'll switch there and then come back to this. But in the interim, let's go make this a free-for-all. If anybody has any questions for anybody else, let's go do that. And if not, I'll throw in some questions. Or Sarah, if you have questions for people, let's go do that. So I'll open it up to the speakers first. If you have questions for each other, let's start with that. Everyone can take themselves off mute. We're gonna test Zoom to its fullest extent. Okay, and then so anyone have any questions for anybody else?
Well, it's not so much a question as how we in the engineering community speak to the public. And the question is the following. Engineering is a collection of quite diverse fields, ranging from aerospace engineering to nuclear engineering and everything in between. And these are all quite different. And each field or each topic has had enormous impact on society. How do we talk to the public in a way that they can see some sort of a unified view of what engineering has done for society. I mean, it's in my talk, I focus mostly on the IT revolution, and then I talked about additive as like, could be the next sort of big thing or would contribute to the next big thing. But I mean, there are different fields were represented in different talks this afternoon, and there are like so many other things that we are not even going to touch today. So the question to the panelists, and you're all leaders, so I'm sure you think about this all the time, is how do we speak to the public given the diversity of fields that comprises engineering?
So, colleagues, I'm happy to make the first answer. Thank you, Pramod, for the question. So let me offer this thought. If the common person does not understand the relevance, then they have no concept of the importance. So half of what I do is what I call drive relevance. There are, my school has 275 researchers, right? I could pick any one of over 500 projects to talk about. But I only talk about the ones that have a physical instantiation and have a direct impact on people. Otherwise, it is too esoteric. Now, this may not be fair. This may not be optimal. And there may be better ways to do it. But my theory is if the common person doesn't understand why this is good, then you'll never, ever be able to get all the support you want. And you have to do that through relevance. So I'll just offer that as a beginning thought.
Anyone else, Maya? Because you're a writer, right?
Sure. So. I will chime in just because my background's in science journalism, and I've been at MIT News since 2014 now. And we, certainly struggle with this, although, our office is definitely a well-oiled machine. We have 5 staff writers who specialize in different fields. Certainly MIT has many schools. We have 5 schools, and some of them are in the humanities, and so we grapple with this topic very often just because of how disparate the fields are that our institution represents. But we have a really great beat system, actually, and our writers are generally science writers, so they're trained in science communications. Just the acronym STEM has helped things along, I think, a lot in the last 10 to even 20 years. When I was growing up, that was not a thing, and people didn't know what engineering. I didn't even know what engineering was when I was in college. I had classmates who were friends of mine, and they were engineering students, and I really did not know what the difference between, let's say, being a physics student or math student. I just know they had like lots of extra P sets, but I didn't know what the applications were, and I didn't know the difference. But I feel like nowadays science communication has grown to include STEM generally, and just little kids start learning about what STEM is much earlier now, and I think that's helpful. But just I think it would be interesting to kind of broaden, when people talk about science communications generally, they usually use the term science communications, even though in many cases they're also speaking about technology engineering. So that could be interesting to kind of have an organization like NAE try to promote, the engineering aspect of communication. I want to say science communications, but I'm kind of reinforcing that issue. Certainly, like I said, at MIT, we try to have people who, some of them have science backgrounds. I actually have a science background myself. Others are more interested in English and writing first, and then come to the STEM fields. But when it comes to training engineers to kind of provide the value and really explain what it is that they're bringing to the world, then, I think it's really important to make sure that their education does include some of that. And I don't know what the requirements are at MIT specifically, but I do know that there are workshops and programs very specifically focused on, encouraging practicum of, explaining your work, even if it is extremely esoteric. I mean, we often have like computer science topics that are not only esoteric in terms of how detailed it is, but they're extremely difficult to illustrate. And in our online world right now, if you can't illustrate something, you're not going to grab people's attention. So that said, we have a strong team of communications collaborators who are in video, who are visual specialists, photographers who actually, many of their photographs end up on the covers of, Nature Materials or whatever it is. So I'm curious to hear what everyone else says, but I think there's certainly work to be done. But if you look at certain places that focus on engineering, like MIT, then I think there are some lessons that can be learned there.
Anyone else want to comment on that? Otherwise, I have some questions from the audience.
I have just one little comment. I mean,
Sure.
One of the things we did, because this was very early on in the 1980s, in the early 1990s, we adopted the comic book format and a comic book character. And because we were dealing with technology that nobody knew about, that was so weird, and the idea that you had to actually know what was going on in a network versus today where you just turn on your computer and pick your Wi-Fi. It was a whole different ballgame back in the day. We tried to get it to the point where it was as simple as turning on a switch, but I think I agree with Al. You have to find a way to make it very simple for people to understand a very complex technology. And for us, it was the idea of a comic book character, because that people sort of gravitated to it. We had a lot of geeky stuff in the comic books that all of my TCP/IP network nerds loved. But at the same time, when you're a teacher or a librarian or just a regular person, you felt like it was maybe accessible to you where it wouldn't have been otherwise.
Great. So the question, and I'm going to generalize it, it was a question from the audience about commercializing the internet, but I'd like to generalize it to commercializing technology and the work that happens in universities. And in particular, get all of your thoughts as to, what's the right balance, right? I think certainly in the time since, I've been in school in the 70s and grad school in the 70s and 80s, I look at what happens in universities and a big push, which I think is good to get it out there and commercialized. But I'd like to hear your thoughts on that. I mean, what's the right balance? And how as we bring, you who are professors, the work you do and your students do, what's the right answer in terms of just commercialization, free will, or, is there some balance that we ought to be focused on?
Can I take that one right from the start? It's an interesting story. So, we had all of those regional networks that I showed on the one slide. We had them all over the United States. And during the 1990s, there was a lot of commercialization talk. And finally, like the phone companies started realizing that if they didn't get on board, they were going to lose. So they started buying up different companies started buying up the regional networks to be commercial. And so pretty much by the end of the 90s, there were very few, if any, there were few, but not very many of the networks that were still around. They had been subsumed by the commercial companies. Then all of a sudden, the R&E people, the universities, were getting really peeved because they weren't getting the service that they were used to. They didn't have the access to the high-speed networks that they were used to. So they're in the late 90s, we rebuilt all this stuff again. And now there's a very active research and education community that's on. Every state has its own research and education network. There's a backbone that's run by internet too. So we went from all R&E to no R&E back to really good R&E on top of partnered with commercial networks for everybody else. So it was, it's like, it was kind of like the idea of the remote server and then the local server and now the remote server and now then the local server and now cloud computing. So, we just seem to go in phases, and the phase we're in right now is that the R&E communities have a very robust network situation, particularly here in California.
Other thoughts on commercialization?
Yeah, I mean, I can make some comments on this. I would say that sort of the major goal is to have research transition to the real world. I think most people can sort of come around to saying, we want our work to have a positive impact on society that supports us. Certainly in engineering, I think people will buy into that. Commercialization then becomes one pathway to getting it done, but not necessarily the only pathway. I mean, in the software space, open source is a big funnel through which academic work can get into the real world. Standards is yet another way in other industries. So I think we have to kind of look at it sector by sector, and I don't know if there is a single template for transitioning research from the lab or from the university to the real world. Second point is, I think Bayh-Dole Act, which was, I think, 1980, just changed the game completely because it gave a stake to the university in its IP. And in a way, even made it responsible for management of that IP. And I think over the last 40 years, we have learned a lot of lessons as to when it works well and when it doesn't work well. And I think in 2022, there is a lot that we can draw on from last 4 decades of experience as to how to make this system of transition from the university to the real world and this collaboration much better. So I'll stop there. There is a lot more to say here. It's a very, very important topic.